So in this lecture, I will discuss eigenvalues of compact symmetric operators. So let me first define compact operators, which is a new object. So I'm assuming here that I have x and y normed space. Note that I'm not assuming them to be linear. So in the definition of compact operators, linearity will not appear. And then we have an operator, A, from a subspace M of x to y. And I will assume, so I'm not assuming here again that M is linear. M is just a subspace of x. And A is defined on this subspace and takes values in another normed space y. And I will say that A is a compact operator if two conditions are satisfied. I will first require that A is continuous. So this means that if I have a sequence xn which is converging to x, both xn and x in M, so that A of xn and A of x are defined, then I will require that A of xn converge to A of x. So this is exactly the usual definition of continuity. Just note that since I'm not assuming that A it's linear, here continuity and boundedness are not related. So I first require A to be continuous, and then I will require a second condition on A, is that if I take any sequence xn which is bounded, so xn in M, bounded, and bounded means, of course, that there exists a finite constant C0 such that the norm of xn is bounded by C0. Then, so if you consider any bounded sequence in M, then AXN, the image, is relatively compact. Right, so this means that I can extract a subsequence from this sequence which converges. So that there exists, so this means that there exists a subsequence nk such that A, x, nk converge to some element y in y. So I will say that an operator A is compact if these two conditions are matched, which means that the first one, that A is continuous, and then that for any bounded sequence xn, then the sequence AXN in Y is relatively compact, which means that I can extract a subsequence which converges. So if these two conditions are matched, I would say that the operator A is compact, and note that I'm not requiring any of these objects to be linear. So let me give you an example of a compact operator. So I will take the interval AB, so one-dimensional interval AB. So here A will be larger than minus infinity, smaller than B, smaller than plus infinity. And I'm considering this space. I want to consider on this space the space of continuous functions defined on AB, and say taking real values. And I have a function f, which is defined on AB square times r, and which is taking values, real values. So f, it's a function of three variables, let's say s, t, and x, and it takes value in R. And I want to define an operator. So my space x and my space Y will be the continuous functions, and I want to define a compact operator going from the space of continuous functions to the space of continuous functions. So the definition of A, so let's consider X to be a continuous function defined on AB. And let me define A from X to X as follows. So you take a continuous function X, and you define of AX at T. So this is a new continuous function, AX, whose value at T, it's given by the following integral. It's an integral from A to B of F S T XS. Yes. So F, I'm assuming here to be a continuous function. So now, since X, it's a continuous function in the interval AB, it is bounded. So actually, in this computation, in this computation of the integral, only the values say that X it's bounded by minus m. So in these computations, only the values of f in the interval ab squared times minus m are important. And since this is a compact and f is continuous, f is uniformly continuous in this space. And by using the fact that f is uniformly continuous, I leave it to you to check that indeed ax is a continuous function defined in the interval ab. So this is the definition of my operator A. You see that A defined in this way is not linear because f it's not a linear function, but in the definition of compact operators, I'm not requiring A to be linear. So I first claim, as I said here, that AX, and I leave it to you to check the details, that AX is indeed a continuous function, an element of CAB. My second claim is that A is a compact operator. So to prove that A is a compact operator, you need first to show that A is continuous, which means that if you take a sequence xn in CAB, and of course in CAB I'm using the norm of a function x is the supremum, and what I claim is that if you consider a sequence xn in, say, a of continuous functions defined in interval ab, which is converging to x in the sup norm, what I claim is that axn converge to a of x in the supreme norm. So I leave it to you to check that this is indeed the case, so that the operator A is indeed continuous. And now I claim that the second property of compact operators is satisfied. And let me recall the statement of this second condition. The second condition is as follows. Well, you take xn, a sequence xn, of continuous function, and you assume that it's bounded. So you assume that there exists a constant C0 such that the sup norm of xn is uniformly bounded by this constant C0. And here again, this condition is telling you that, well, in the definition of A, only the values of f in the compact set ab squared times minus mm or minus c0, c0 are important, so that f is uniformly continuous. So by using the fact that this f is uniformly continuous, what I claim is that you can show that the family AXN is equicontinuous. So my claim is that, and I leave it to you to prove, is that since f is uniformly continuous, then AXN, and let me call this sequence yn, so it's a sequence of continuous function, and what I claim is that this sequence yn is equicontinuous. Once you prove that this sequence is equicontinuous, then you can use classical theorems as the Laasculi theorem to show that you can find a subsequence y and k which converge in the sup norm. So I leave it to you to check that this sequence is indeed equicontinuous, and from this equicontinuity you can deduce that A is a compact operator. So we have here an example of an integral operator which is nonlinear but which defines a compact operator, and which will appear later in these lectures. Now that I have defined what is a compact operator, and now that I gave an example, let us go back. So I have here X, a Hilbert space. Let's say Y also, a Hilbert space. And we have an operator A, which is defined in a linear subspace of X, taking values in Y. So dA is a linear subspace of X. And I'm assuming that A is symmetric and now compact. Symmetric, if you recall, one of the conditions of symmetry is that the operator is linear. So I'm assuming that this operator is linear. Compact, one of the conditions of compacity is boundedness, its continuity. But we have seen that if an operator is continuous and linear, then it's bounded. And once it's bounded, another property of symmetry is that the space, the domain of the operator, it's dense. And we have seen that if we have an operator which is linear, bounded, and defined on a dense subspace, we can extend it to the whole space X in a unique way. So as soon as I'm talking about symmetric compact operators, I will consider A to be defined in the whole space, because if it's not, I can always extend it in a unique way to the whole space. So from now on, I'm assuming that I have X a Hilbert space. A will be an operator from X to X. Which is symmetric. And compact. Compact I just defined, so I won't remember you the definition of compact. Symmetric, let me remind you that we'll first require the operator to be linear. Then we require it to be defined on a dense subspace, but here I'm taking the whole space. So the domain of definition, it's indeed dense. And then the last condition of symmetry is that AXY it's equal to XAY for all X, Y in X. So I have an operator which is compact and satisfies these conditions for all points X, Y in my Hilbert space X. Now I will prove a theorem in which I require this Hilbert space to be separable. So remember, separable means that you have a basis which is countable. So I'm assuming that X admits a basis, an orthonormal basis, which is separable. And with these conditions, so with these assumptions, we will prove the following theorem. Well, we will prove that, so let me just recall to make sure that the theorem is clear. What are the assumptions? I'm assuming that X, it's a separable Hilbert space. So X, a separable Hilbert space. And I'm assuming that on X, I have an operator A from X to X, which is compact and symmetric. And under these two conditions, I will state now a theorem which I will prove in the remaining part of this lecture. So the main theorem of this lecture reads as follows. So recall X, it's a separable Hilbert space. A, it's a compact symmetric operator from X to X. Then what I claim first is that there exists a not orthonormal basis xj of eigenfunctions. So each xj is an eigenfunction of my operator A. So that's the first claim. Then the second claim is that, well, if you take one, let me call lambda j the eigenvalue associated to the eigenfunction xj. So if lambda j is different from lambda k, then xj and xk are orthogonal. Then what I claim is that the lambda j has, well, let me state it in this way. Let me take lambda, an eigenvalue of A, the operator A. So remember, an eigenvalue of A means that there exists x different from 0, such that Ax is equal to lambda x. So if you take any eigenvalue of this operator A, what I claim is that it has finite multiplicity. Which means that if you take the space of all eigenfunctions associated to lambda, so you take the space of all x in X such that Ax it's equal to lambda x. So this is a linear subspace of X. What I claim is that the dimension of this space is finite if lambda is different from 0. So take an eigenvalue which is different from 0 of A. Consider the space of eigenfunctions associated to lambda, so all solutions to this equation. This is a linear subspace. What I'm saying is that the dimension of this linear subspace, it's finite. This is what finite multiplicity means. And finally, let's assume that the dimension of my space, it's infinite. Of course, here, to have a non-trivial statement, I'm always assuming that this Hilbert space X is different from 0. Right? Well, this I will never repeat. I'm always assuming that X is non-trivial. So now let's assume that the dimension of X is plus infinity. Then there are two possibilities. Either there is only a finite number of eigenvalues different from 0. So here, I'm saying that I have an orthonormal basis and that all eigenvalues have finite multiplicity. Now, I'm talking about different eigenvalues. Either you have a finite number of eigenvalues, which are different from 0, or a second possibility is that these eigenvalues, lambda j, converge to 0. So you might have a countable number of eigenvalues, but these eigenvalues are converging to 0. And here, let me mention that, well, these are xj forms an orthonormal basis, that if lambda is an eigenvalue, it has to be one of these lambda j's. So besides proving that if lambda is an eigenvalue of A, it has finite multiplicity, I will also prove that if it's an eigenvalue, then lambda it's equal to one of these lambda j's, which are the eigenvalues associated to this orthonormal basis. So this is the statement. So let me just state it again. I'll prove that you can find in this Hilbert space an orthonormal basis. That we can always do. But we can find a special one, which is made of eigenfunctions of A. Remember that with the Gram-Schmidt procedure, you can always, in a Hilbert space, a separable Hilbert space, find a countable basis, orthonormal basis of the space. But here, what's special about this case in which we have a compact symmetric operator is that we can find a basis made of eigenfunctions of A. Then, something we already proved, if you take two different eigenvalues, lambda j and lambda k, different eigenvalues of the operator A, then the associated eigenfunctions are orthogonal. Then a third statement is that if you consider any eigenvalue of our operator A which is different from 0, then it has finite multiplicity, which means that the dimension of this space is finite, and also that lambda is equal to one of these lambda j's. So to each eigenfunction you have an associated eigenvalues. So all the eigenvalues are one of these ones. And finally, if you assume that the dimension of our space is infinite, there are two possible cases. Either you have only a finite number of eigenvalues which are different from 0, so that you have eigenvalues lambda 1 up to lambda n for a fixed n. Or if you have a countable number, of course you can't have more than countable because here we already proved that there is at most a countable. Or you may have a countable number of eigenvalues, but in this case the limit is equal to 0. So the proof of this theorem, it's made in several steps. So I will first assume that the following assumption holds. I will assume that if Ax it's equal to 0, then x is equal to 0. So that the null space of my operator A is just the point 0. So I'll first prove the theorem under this condition, and then I will remove this hypothesis. And under this condition, the theorem will be proved in several steps. So step 1 is as follows. I'm assuming that x is different from 0. So there exists an x different from 0 in X. AX, well, is not equal to 0 due to this assumption. So the norm of AX, it's positive. So this means that the norm of A is really positive. So this assumption implies that the norm of A is really positive because I can find x different from 0 for which the norm of AX is really positive. Now my claim is that there exists x in X. So let me call that maybe x1 in X, which has the following property. It's an eigenfunction. So AX equal to lambda x for some lambda, and this lambda satisfies that its norm it's equal to the norm of A. So what I want to prove is that there exists an element of X, which I'm calling x1, which is an eigenfunction. So AX1, it's equal to lambda x1 for some lambda. And this lambda has the following property. Its absolute value, it's equal to the norm of A. So let me prove this claim, which is the content of step 1. We proved in the previous lecture that the norm of A can be expressed as the supremum over all x with norm equal to 1. So I forgot to say here that the norm of x1 is 1. So the norm of A, it's given by the supremum over all x whose norm is equal to 1 of AX x. Now, well, this is finite because A is bounded. So I can find a sequence xn which approximate this supremum. So there exists a sequence xn, or let me call it zn, such that A zn converge to the norm of A. And I can take these zn's with norm equal to 1. Now, observe the following, is that this is a sequence of real numbers. Its absolute value is converging to this. So either this sequence, I can find a subsequence AZN, which is converging to A, or AZN is converging to minus A, right? So there exists a subsequence NK such that A ZNK, it's converging to A, or it's converging to minus A. Okay. Well, I will assume without loss of generality, all the arguments work the same. I will assume that there is a subsequence which is converging to the norm of A, and I will denote this subsequence still by n, so I can extract a subsequence which I'm still representing by Zn, such that AZN, Zn, the scalar product of AZN with Zn is converging to A, and this is what I'm calling lambda 1. So you see that lambda 1 indeed has norm equal to the norm of A. Now, what I claim is that lambda 1 Z1 minus A Zn, that this is converging to 0. I'll prove this claim. So what I know is that AZN Zn, it's converging to lambda 1, and now what I want to show is that lambda 1 Z1 AZN minus AZN, it's converging to 0. Why is that so? Well, 0 is of course less or equal than lambda 1 Zn minus A Zn norm square. But this is equal to the scalar product of this expression with itself. So this is lambda 1 Zn minus A Zn, lambda 1 Zn minus A Zn. So let's compute this scalar product. So we have the diagonal terms. So since Zn has norm equal to 1, the first diagonal term gives me lambda 1 square. And the second diagonal term gives me the norm of A Zn square. And then we have the off-diagonal terms. So this is lambda 1 minus lambda 1 A Zn. And I will use the fact that A is a symmetric operator just to put A on the other side. So I have minus lambda 1 A Zn Zn. So this is this one, and then I have this one, which is exactly the same because lambda 1, it's a real number, so I don't get the complex conjugate here. So I have a 2 because I have two terms which are equal. Now this is bounded. I can use the fact that the norm of A Zn, it's bounded by the norm of A times the norm of Zn. The norm of A, it's equal to lambda 1. So here I get that this is bounded by lambda 1 square times the norm of Zn square. But the norm of Zn is 1. So I get here 2 times lambda 1 square minus 2 times lambda 1 A Zn Zn. And A Zn Zn is converging to lambda 1. So this term is converging to lambda 1 as n tends to infinity. And I get 2 times lambda 1 square minus 2 times lambda 1 square. So this is converging to 0. And, well, and therefore this expression, which is positive, it's converging to 0. And this is exactly what I claimed. So we proved that lambda 1 Zn minus A Zn, it's converging to 0. That's fine. So this is a first claim. Now, the sequence Zn, it's bounded. So let's use the fact that A, it's a compact operator to extract. So since the sequence Zn, it's bounded, the sequence A Zn, it's relatively compact, which means that we can extract a subsequence of Zn such that A Zn converge. So I know that A Zn, it's converging to some expression, some point. Okay, that there exists a subsequence, such that A Zn, it's converging to some y. Fine. So let me represent still the subsequence by Zn. So I have that A Zn, it's converging to y. Since A Zn, it's converging, and lambda 1 Zn minus A Zn, it's converging, this means that lambda 1 Zn, it's converging. And since lambda 1 is different from 0, because lambda 1 is the norm of A, and the norm of A is strictly positive, this means that actually Zn is converging. So Zn, it's converging. So we deduced from the fact that this sequence converge, and from the fact that A is compact and Zn has norm equal to 1, that actually Zn converge. So Zn converge to x1. This means that A Zn, because A, it's compact and therefore bounded, A Zn converge to Ax1. And from this limit, since Z1 it's converging, Zn is converging to x1, we get that lambda 1 x1 minus A x1, it's equal to 0, which means that x1 is eigenfunction of A associated to the eigenvalue lambda 1. x1 has norm equal to 1 because Zn has norm equal to 1. So we proved exactly the claim. We proved that there exists an x1, which is an eigenfunction, whose norm is equal to 1, and the eigenvalue associated to this eigenfunction has absolute value equal to the norm of A. So this proves, this completes the proof of step 1. So I'm assuming this hypothesis, and I just proved that there exists an x1, which is an eigenfunction, has norm equal to 1, and the eigenvalue associated, which now I'm calling lambda 1, is such that its absolute value is equal to the norm of A. So now let's go to step 2. Let me represent by L of x1. This is the linear space generated by x1, so the linear space of all linear combinations of x1, which is very simple. Now let me take the orthogonal space of Lx1, which I'm calling L1 perp. So this is the space of all y in X, which are orthogonal to x1, so that's such that y x1 it's equal to 0. And, well, my claim is that A, so this is a linear subspace of X, so I can take its restriction, the restriction of A to this linear subspace. Let me call A1 the restriction. So A1 of y, it's equal to A of y for all y in this space Lx1 perp. And my claim is that A1 of Lx1 perp, it's included in Lx1 perp. So actually, A1 is compact linear symmetric operator from Lx1 perp to Lx1 perp. So let's prove that. So let me take a y in Lx1 perp. Which means, so this means that y it's orthogonal to x1. And let's prove that A1 of y belongs to this same space. So to prove that A1 of y belongs to this space, I have to show that A1 y is orthogonal to x1. But A1 of y, by definition, it's A of y. And since A is symmetric, AY x1, it's y AX1. X1 is an eigenfunction, so this is equal to lambda 1 y x1. And x1, it's orthogonal to y, so this is 0. And this shows that indeed A1y belongs to Lx1 perp. So actually, this operator, it's an operator from Lx1 perp to Lx1 perp. And now I leave it to you to check that this operator is symmetric and compact. This is A1 is symmetric and compact. And this follows from the fact that A is symmetric and compact. That's a two-line proof, so I leave it to you. And what I want to show is that this condition is satisfied. So let me assume, of course, maybe the space is one-dimensional. Maybe x1 is generate the whole space, and therefore Lx1 is the empty space. But let me assume now a second assumption that the dimension of x, it's infinite, and then I will consider the case, which is, this case it's more difficult, and then afterwards I will consider the case in which the dimension is finite. So let's assume that the dimension is infinite, which means that the dimension of this space is also infinite, and I'm claiming that this condition is satisfied by A1. So let's assume that A1 y it's equal to 0, but by definition this is A of y, so A of y is equal to 0, and therefore y is equal to 0. So this condition, this hypothesis is also satisfied by A1, and therefore I'm back at exactly the same situation that I had previously in step 1, because since the dimension of x is infinite, L x1 perp is different from 0. If it were equal to 0, this means that the space x will be equal to the space generated by x1, and that will contradict the fact that the dimension of x is infinite. So we are back as at the same, we have all the hypotheses we had before at step 1, in which we had an operator which is symmetric and compact, defined on a space which is different from 0. So we can repeat step 1. And find x2, which is an eigenfunction of A1. So x2 in L x1 perp, such that the norm of x2 it's equal to 1, and A1 x2 it's equal to lambda 2 x2, where the norm of lambda 2, the absolute value of lambda 2, it's equal to the norm of A1. Right. Well, but here, by definition, A1 of x2, it's A. So this is equal to A of x2. So we have, by repeating step 1, we can find, step 1 provides us with an element x2 in Lx1 perp, such which is an eigenfunction of A associated to the eigenvalue, a new eigenvalue lambda 2, where lambda 2 is now the norm of A1. And what is the norm of A1? Well, this is the supremum over all z with norm equal to 1, z in the space, so our space now it's Lx1 perp, of the norm of A1z, but A1z, it's A of z. So the absolute value of lambda 2, it's given by the supremum over all z in Lx1 perp with norm equal to 1 of the norm of Az. And this is, of course, smaller than the norm of A, because we are taking this supremum in a small set. And A, it's given by lambda 1, so this is equal to lambda 1, the absolute value of lambda 1. So this second eigenvalue which we found, so lambda 2 is the eigenvalue associated to x2, it has the property that it is bounded by the first one. So in conclusion, by repeating step 1, by applying step 1 to the operator A1, we can find a new eigenfunction, which I'm calling x2, which has norm equal to 1, and whose eigenvalue has absolute value bounded by lambda 1. And since the last property which I want to mention is that x2 belongs to Lx1 perp, which means that x2 and x1 are orthogonal. Right? So let me write the conclusions. I'm assuming that the dimension of x now it's plus infinity. And in the second step, I obtained a new eigenfunction, x2, which is orthogonal to x1, which has norm equal to 1, and such that the eigenvalue associated, which I'm calling lambda 2, is such that the norm, the absolute value of lambda 2, is bounded by the absolute value of lambda 1. And remember, the absolute value is strictly positive, right? Because this norm, the norm of A1, is strictly positive. So this is our conclusion after the first step. And now we can iterate this argument. So iterate this argument in which sense? Well, instead of considering now the linear space generated by x1, I can consider the linear space generated by x1 and x2 and call that Lx1, x2. So these are all linear combinations of x1 and x2. I can consider the orthogonal space of this space. So these are all points in X which are orthogonal to x1 and x2. And reduce and consider the operator A restricted to this space. Repeat this argument to show that A2 actually sends this space into itself. And now repeat the argument to find a new, by using the fact that the dimension of X is plus infinity, we can repeat this argument to find a new eigenfunction, which is now associated to an eigenvalue lambda 3, whose absolute value is strictly positive and less or equal than lambda 2. So that my step 2, I can now state my claim, which I just proved by induction. Is that, well, by assuming that the dimension of my space is plus infinity, then my step 2 claims that there exists a sequence xn of eigenfunctions. So xn has norm equal to 1. Xn is an eigenfunction associated to an eigenvalue which I'm representing by lambda n. Xn and xj are orthogonal if j is different from n. And we have the following relation. Lambda j, it's strictly, well, it's less so, it's strictly positive and less so equal than the norm of lambda j minus 1 to the norm of lambda 1, and this lambda 1 is equal to the norm of A. So this is the conclusion of this induction argument, that we can find a countable sequence xn of eigenfunction. These eigenfunctions have norm equal to 1. They are orthogonal among themselves, and the associated eigenvalues are decreasing in absolute value. They are all strictly positive, and the first one has absolute value equal to the norm of A. So I just recall here what we proved. We proved that we have a countable family xn. I'm assuming that the dimension is infinite. We have a countable family of eigenfunctions xn. I'm calling lambda n the eigenvalues. These eigenfunctions have norm equal to 1. They are orthogonal 2 by 2. And the eigenvalues are decreasing. So the absolute value of the eigenvalues are decreasing. The largest one has absolute value equal to the norm of A. And they are all strictly positive. So now what I claim in step 3 is that these eigenvalues converge to 0. So they are strictly positive. Well, they could be converging to a strictly positive constant, what I will prove is that actually they are converging to 0. And the proof is based on the fact that A is a compact operator. So assume that this is not true, and we will find a contradiction. So assume that lambda n is strictly larger or equal than epsilon, which is a strictly positive constant. So if this is the case, then what you know is that if you take the norm of xn divided by lambda n, that this is bounded, well, by 1 over the absolute value of lambda n times the norm of xn, but the norm of xn is 1. And since lambda n is really larger than epsilon, this is bounded by 1 over epsilon. So this family here, it's a bounded family. And since A it's a compact operator, this means that AXN divided by lambda n, this is relatively compact. But AXN, well, by linearity, this is 1 over lambda n times A of xn. Xn, it's an eigenfunction, so AXN, it's lambda n xn. So the lambda n cancel with that lambda n. And this, what we obtain is that this is equal to xn. So what the compactness of A tells us is that the sequence xn is relatively compact. But this can't be, because if you consider xn minus xm square, so this is xn minus xm, xn minus xm, well, you have the diagonal terms, which gives you 1 because the xn have norm equal to 1. So you have 1 plus 1, the two diagonal terms. And then you have the off-diagonal terms, but since xn are orthogonal, they are 0. So this gives you 2, and therefore this sequence any subsequence cannot converge, because if you take any two different terms, they are at distance 2. So this sequence any subsequence will never be a Cauchy sequence, and therefore this sequence, any subsequence, will not converge. So it's not true that xn is a relatively compact sequence, and therefore we get a contradiction by assuming that lambda n is larger or equal to a strictly positive constant epsilon. So this proves that lambda n converges to 0. So we just proved that lambda n converges to 0. I added this property, and now I want to start proving that this xn forms a basis of our space. So in step 4, what we will prove is that for any x, we have the following identity, that A of x, it's equal to the sum for n larger than 1 of xj times lambda j. So I claim, and of course here I'm summing over j. So xj is a orthonormal family. So this, since lambda j, it's bounded, because all these lambda j's are bounded, so the right-hand side, it's well defined. You can compute the partial sums, compute the norm of the scalar product or the square of the norms of this partial sum, and show that this is bounded. So that will make this family of partial sums form a Cauchy sequence, and therefore the limit, it has a limit, and the limit is represented by this infinite sum. So what I'm claiming is that the right-hand side, which is well defined, it's equal to the left-hand side. So let's prove that. So let's fix an x in x, and let me consider zk to be x minus the sum from 1 up to k of x, xj, xj. And what I claim is that zk is orthogonal to xm for m between 1 and k. And this is clear because, well, let's take the scalar product of zk with xm. So this is equal to, by linearity, xm minus the sum from j equal to 1 up to k of xj, xm. So I'm just using linearity. We know that these vectors or these points are orthogonal. So this is equal to 0 unless j is equal to m. And if j is equal to m, this is 1. So let me represent that by delta jm to say that this is 0 if j is different from n and equal to 1 if j is equal to m. So that means that this sum, well, here I'm taking m between 1 and k, so that this sum, only the term j equal to m will survive, and so that will give me xm minus, I have 1 when j is equal to m, so this gives me minus xm, and this is indeed equal to 0. So we proved that the scalar product of zk with xm, it's equal to 0 for all m between 1 and k. Now remember, I have the linear space generated by x1 up to xk. So this is the linear space. Remember, in step 2, we introduced that space, the linear space generated by x1 to xk. And we have the orthogonal to that space. And we defined ak in this space. So ak goes from this space to itself. And the norm of ak, it's equal to the absolute value of lambda k. Right? So this by our construction. Moreover, ak of y, it's equal to a of y for all y in this space L x1 xk perp. So this was the definition of ak. ak was equal to the restriction of a to this space. So we just proved that this element zk is orthogonal to all xm from m from 1 to k. So zk actually belongs to that space. We proved that zk belongs to L x1 xk perp. Thus, this means that if I take a of zk, since zk belongs to this space, a of zk is equal to ak of zk. And this is bounded by the norm of ak times the norm of zk. The norm of ak, it's the absolute value of lambda k. And I claim that the norm of zk, it's bounded, so I won't use this anymore. So let me erase it. And I want to compute zk square. Well, So zk by definition it's equal to, let me call this element yk. So what I'm saying is that zk it's equal to x minus yk. This is bounded by the norm of x plus the norm of yk. And if you compute well, you know that by Bessel inequality that the norm of this is bounded by the norm of x. Or by a direct computation, you can show that the norm of yk is bounded by computing the square of the norm. You can show that the norm of yk is bounded by the norm of x. So we have that the norm of zk is bounded by 2 times the norm of x. And so this is bounded by 2 times lambda k times the norm of x. And we know that lambda k converges to 0, so this expression is converging to 0. So we proved that a zk converges to 0. So we showed that a zk is converging to 0. But a of zk, it's equal of ax minus, by linearity, this becomes this sum, this expression times axj, but axj, it's equal to lambda jxj. So this is minus sum from 1 up to k, x xj, lambda j xj. So this is converging to 0, and this means that this expression here, it's converging to ax, but this expression, as I send k to plus infinity, it's exactly what I mean by this infinite sum. So this expression is converging to this infinite sum, and it's also converging to ax, which means that ax it's indeed equal to this infinite sum. And this is our claim in the 4th step. So we just proved that for all x, ax it's equal to this infinite sum. Now I want to remove a and lambda j from this expression. I want to show that for any x, x it's equal to that infinite sum. So that would say, if we can prove that, this would tell me that xj is indeed a basis of x for the space x, because any element of x can be written on this basis by this formula. Well, the proof of this identity is pretty elementary. Let's call y this sum. So because the xj's are, so I'm fixing x, I'm considering this infinite sum, and I'm saying again that this infinite sum is well defined as the limit of the partial finite sums, because the partial finite sums form a Cauchy sequence, and therefore this infinite sum represents the limit of this Cauchy sequence. And I'm calling this limit y. And I want to show that y it's equal to x. Well, what I claim is that ax it's equal to ay. And why is that? Because, well, by linearity, if you have here a partial sum, so these partial sums are converging to y, by continuity, a of the partial sums are converging to a of y. And a of the partial sums are equal to, well, by linearity, this is x, xj, axj, but axj, it's lambda j, xj. So this is a of the partial sum, and since a is bounded, these partial sums are converging to a of y. So we have that I want to prove that AX is equal to AY. Right? So this is what I want to prove. AY is given by this expression, but now by the previous step I know that this infinite sum is equal to AX, and this is exactly what I wanted to prove. And this means that AX minus Y is equal to 0, and it follows from our condition that this implies that X is equal to Y, which proves that this infinite sum is indeed equal to X, and this is what we wanted to prove. So I wrote what we just proved. We proved that for any X in X, X can be represented on the basis Xj by this infinite sum. So this means that Xj is an orthonormal basis of our space, since any element can be written on that basis in this way. So the last step in our proof is to show that if I take lambda an eigenvalue, then it has finite multiplicity. So let me take lambda an eigenvalue. So this means that there exists X different from 0, such that AX is equal to lambda X. And I want to show that the dimension of this space is finite. So that so this is what I want to prove now. Let me start from the formula we just obtained. I know that X it's equal to the sum for j larger than 1 of X, Xj, Xj. Now, I know that lambda X is equal to AX. So let me write what is lambda X. Lambda X is the same expression multiplied by lambda. And let me write what AX is using linearity. So if I apply A by linearity, since Xj it's an eigenfunction associated to the eigenvalue lambda j, this is AX. It's equal to the sum of X, Xj, lambda j times Xj. Now, by saying that lambda X and AX are equal, what I get is that the sum of lambda j minus lambda X, Xj, Xj, that this is equal to 0. Well, and since the Xj are orthonormal, for this sum to be equal to 0, I need all these terms to be equal to 0. If one of them is non-zero, by computing the square of the norm of this object, you obtain something which is strictly positive. So since this is 0, this tells me that lambda j minus lambda X, Xj, that this is equal to 0 for all j. And this means that, well, that if lambda j is different from lambda, then X, Xj is equal to 0. X is orthogonal to Xj. Okay. So the first conclusion is that, well, there should be one lambda j which is equal to lambda. Because if all lambda j's are different from lambda, this means that X is orthogonal to all Xj, so that this expression is 0. And from this expression, we conclude this is 0 for all j. We conclude that that X is equal to 0, but we know that X is different from 0. So from the fact that if lambda is different from lambda j implies that X, Xj is equal to 0, and from the fact that X is non-zero, we conclude that, well, there should be one lambda j which is equal to lambda. So there is at least 1j for which lambda j is equal to lambda. So this proves that, well, all the eigenvalues are one of these lambda j's that we obtained, that we constructed. And moreover, it tells us, well, that in this sum, I have to sum only over the indices j for which lambda j is equal to lambda. So this sum, the sum, it's made of all j larger than 1, for which lambda j is equal to lambda. But how many j's can be equal to one fixed number lambda? Well, since the lambda n's are going to 0, this sum, it's finite, right? Since the eigenvalues are converging to 0, you may have at most a finite number which takes a value lambda. So this sum, it's finite. It's over a finite number of terms. And this means that the space, the functions x, the solution of this space, can all be written over a finite number of xj's, which means that the space made of solutions of this equation, it's finite dimensional because any solution can be written as a finite linear combinations of xj's. So this proves that indeed you have a finite multiplicity, which, as I said, finite multiplicity means that if you look at this space, which is a linear space, the dimension of this linear space is finite, and the dimension is finite because any element can be written as a finite linear combinations or a finite number of orthogonal points xj. So this completes the proof of the theorem under the assumption h, so that x equal to 0 implies x equal to 0, and that the dimension is infinite. So let me first remove the assumption that the dimension is infinite. Let's assume that the dimension of x is finite, and that, but I still keep the assumption that ax equal to 0 implies that x is equal to 0. Well, but this is the proof here. It's exactly the same as the one before. Remember, we first constructed x1, which was associated to an eigenvalue lambda 1, whose absolute value was equal to the norm A. Then, starting from this, we consider the space L of generated by x1. We took its orthogonal space, and at this point, well, either this space is the space 0, or it's a space different from 0. If this is the space is 0, then it's, well, we're finished, because this means that x is actually L of x1, the space generated by x1. If it's not the space generated by x1, this means that this orthogonal space is different from 0, and by repeating the previous proof, we can find a second element x2, a second eigenvalue lambda 2, so x2 it's an eigenfunction, which has exactly these properties, and once we have x2 and x1, we define the space generated by x1, x2. Either this space is equal to x, or it's not. If it's not, this means that the perpendicular space is non-zero, and we can repeat. Since the dimension is finite, at a certain point, we will find that x is the space generated by Lx1 up to xn, and that these points x1, xn are eigenfunctions with norm equal to 1. They are orthogonal 1 by 1, and the finite number of eigenvalues have absolute value which are decreasing. So we don't have the convergence to 0 because we have only a finite number, and since the space x is the one generated by x1, xn, this formula is still valid, but now the sum is a finite one because the space is finite dimensional, and the fact that the eigenvalues all eigenvalues are the space generated by these eigenvalues. The eigenspaces are finite dimensional, so that the fact that these eigenvalues have finite multiplicity is obvious because the space has finite dimension. So the case in which the situation in which the dimension of the space is finite follows from our previous argument. The only difference is that at some point we will stop our construction because X will be the space generated by a finite number of these eigenfunctions. So finally, let's remove this assumption. So we have an operator A acting from X to X. Let me represent by n of A the null space of A. So this is all points X in X, such that A of X is equal to 0. Well, you can show, of course, that NA, it's a closed linear subspace, that it's linear follows from the linearity of A, that it's closed follows from the continuity of A. So it is a closed linear subspace. And it's also separable, because X is separable, and N of A, it's a linear subspace of X. So we have here NA, which is a Hilbert space, which is separable. So we know that we can find a countable orthonormal basis of NA by the Gram-Schmidt algorithm. So there exists a family, let me call it Wj. J, this sum, I will write it as an infinite sum, but it might be also finite. It depends on the dimension of NA. These Ws have norm equal to 1. They are orthogonal. And any element n, if y belongs to the null space n of A, then y can be represented as y Wj, Wj. And again, I'm writing this sum as an infinite sum, but it might be a finite depending on the dimension. So this follows just from the fact that we have a separable Hilbert space. So we have seen how to construct a countable orthonormal basis of a Hilbert space through the Gram-Schmidt method. So this is for NA. Now, I know that since NA it's a closed linear subspace, that X can be written as this space plus the perpendicular space. So remember that, well, I define what this space means, and this sum means that any point in X can be represented as a sum of one point in this space and another point in this space, and that this representation is unique. In particular, the intersection of NA with this space is the point 0. So at NA we have a basis, which is given by the W's. So now I will look at this space. NA perp, we proved it's a closed linear subspace of X. And let's see its properties. The first point, I claim that if I take an element in this space, I apply A to this element, this new element still belongs to this space. So let me make it precise. Let's assume that X belongs to the perpendicular of NA. What I claim is that AX also belongs to the perpendicular of A. So let's prove that. That's easy. What defines this space? Well, this is the space of all points Z, such that Z is orthogonal to all elements of NA. So let's take X in this space. This means that X is orthogonal to Y for all Y in NA. I want to prove that AX belongs to NA, perp. So to prove that AX belongs to NA perp, I have to show that AX is orthogonal to any point Y in NA. So let's consider a point Y in NA. By symmetry, this is X AY. But now Y belongs to the null space of A. So AY is 0. So this is X 0, and this is 0 because the scalar product of any element with 0 is 0. And therefore, AX is indeed orthogonal to any element of NA, and therefore AX belongs indeed to NA perp. So what we proved is that our operator actually sends NA perp to NA perp. So let me call its restriction as A perp. So A perp, it's a new operator from NA perp to NA perp, which is the restriction of A to this space. So NA perp, this space, it's a separable Hilbert space. It's a Hilbert space, that's obvious. It's separable because it's a subspace of X, and X is separable. And now what I claim is that the assumption holds for the restriction. So what I claim is that A perp X equal to 0 implies that X equal to 0. Right? Well, why is that so? Assume that A perp of X, it's equal to 0. So I'm taking X in NA perp, right? Because this operator is defined only in NA perp. I'm taking X in NA perp, and I'm assuming that A perp of X is equal to 0. I want to conclude that X is equal to 0. So I know that A perp of X is equal to 0, but A perp, it's the restriction of A to X to NA perp. So this means that AX is equal to 0. And AX equal to 0 means that X belongs to the null space of A. So X at the same time belongs to the null space of A and to the perpendicular, the orthogonal piece of NA. And we have seen that the intersection of these two sets is 0. It's the element 0, so this implies that X is equal to 0. And this is exactly what we wanted to prove. So the restriction A perp of A to this space satisfies this hypothesis. And therefore, there are two possibilities. Either this space is a finite dimensional space, in which case, so now I'm looking at NA perp. Either this space is finite dimensional, in which case we can apply the previous theorem to the finite dimensional in the finite dimensional situation, for which we find x1, xn, which are eigenfunctions associated to the eigenvalues lambda 1, lambda n, in which this inequality is satisfied, and lambda 1 it's equal to the norm of A perp. And well, here we have a basis, an orthonormal basis of eigenfunctions of this space. If we add this orthonormal basis to the one of NA, we get a family of orthonormal eigenfunctions, because, well, I can assume that W1, W2, and so on are eigenfunctions associated to the eigenvalue 0. So I get a basis, an orthonormal basis of the space X, right? the x1, xn are orthogonal to the yj's. Because these two spaces are orthogonal, yj belongs to an A, and x1 to this orthogonal space. So we complete the proof. We have a finite or countable family of wj's which are sent to 0, such that A of wj is equal to 0. And then we have a finite number of eigenfunctions associated to non-zero eigenvalues. The second possibility is that this space is infinitely dimensional. And therefore, by the first part of the proof, we find this family xn, which forms a countable basis of this space NA_perp. And by adding to this family dw, we get a countable family of orthonormal bases made of eigenfunctions, an infinite number associated to non-negative, non-zero eigenvalues with these properties, and a finite or an infinite family, countable family of elements which form the basis of NA. And so this completes the picture. So you see that if the operator is symmetric and compact, we can decompose our space in a basis of eigenfunctions. And these eigenfunctions have the following property. If you consider the eigenvalues associated to it, they are bounded and they are converging to 0. So each one has finite multiplicity. And so this is essentially a way to construct a basis in which A becomes a diagonal operator, right? A in the direction xn acts as a product of the identity as lambda n times the identity, which means that compact symmetric operators are very simple. They are essentially, you can decompose your space in directions, and in each finite dimensional space, A acts as a product of the identity. So this completes the proof and the lecture and this lecture.